want to get a picture beforehand, or? Oh, okay. Specific about what it was. Thank you.
Okay.
Just
Flow.
good morning. Good morning, and thank you all for attending our final award session of the summer meeting. It is my distinct pleasure to announce the award of the 2018 Klopsteg Memorial Lecture Award to Dr. Clifford Johnson. Dr. Clifford Victor Johnson, University of Southern California, Los Angeles, is the 2018 recipient of the Klopsteg Award. Dr. Johnson graduated with a bachelor degree of science in physics from Imperial College London. In 1989, he completed his PhD in physics at the University of Southampton in 1992. He is a theoretical physicist and a professor at the Department of Physics and Astronomy of the University of Southern California. He previously worked as a postdoctoral researcher at the Kavli Institute for Theoretical Physics at the University of California, Santa Barbara, and at the Institute for Advanced Study, Princeton, and held professorships at the University of Durham, the University of Kentucky. He received a National Science Foundation Career Award in 1997. In 2005, Dr. Johnson received the Maxwell Medal and Prize for Theoretical Physics from the Institute of Physics. And the award read for his outstanding contribution to string theory, quantum gravity, and its interface with strongly coupled field theory, and in particular for his work on understanding the censorship of singularities and the thermodynamic properties of quantum space-time. If you understand that, you are far better than I am. In 2005, the Journal of Blacks in Higher Education listed Johnson as the most highly cited black professor of mathematics or a related field at an American university or college. In 2015, he was awarded a Simmons Research Fellowship. He is well known for explaining the physics to the general public through public lectures, writing, drawing, blogging, filmmaking, appearances at museums, bookstores, festivals, and especially through television and online. His most recent book is a nonfiction graphic novel entitled The Dialogues, Conversations about Nature of the Universe, printed by MIT Press. He works with artists, writers, filmmakers, and others to help improve science, content, and the perception and understanding of science in the arts, media, and the broader culture. He regularly appears on and advises several shows internationally on various TV and online channels, and is particularly well known as one of the co-presenters of the longest-running TV show about physics and astronomy, The Universe, the movie Einstein, and for his work on shows like The Fabric of the Cosmos and The History of the World in 2 Hours. He gave a TED Talk in 2012 entitled String Theory and the Hidden Structures of the Universe, and a Pop Tech Talk in 2017 entitled Adventures in Science and Culture. I admit, you exhaust me just reading your bio. I mean, it is incredible. I don't know how you find time to do that. It is my distinct pleasure to present the 2018 Klopsteg Award to Dr. Clifford Johnson.
Thank you very much. It's a real honor to receive this, especially from this organization that I think is really definitely what I like to consider as my people, dedicated to getting people excited about physics. So I thought I would maybe do something a little different from what you're used to and tell you a little bit about some of the ideas that are exciting in areas of black hole physics, just for fun, and then take a sidestep and talk about how some of those aspects of physics, our understanding of space and time, and some of the wonderful things that can happen are in our everyday lives in the context of our entertainment. Because increasingly, those of you who spend time watching TV shows and movies and things like that, increasingly you'll see that some of these concepts are maybe not always accurately used, but at least they're part of the fabric of storytelling that's used a lot to entertain. And that actually is a great lead-in for people to really engage with the science. So I'll talk a little bit about maybe how I do some of that in the context of consulting with people in the industry of entertainment. So I'll just set a little timer here so I don't run over, because I am running on a little bit of jet lag here, so I just want to make sure. So the key idea I want to talk about is, of course, the whole business of space and time. And so I'll just remind you of some of the ideas, and I apologize if you're very familiar with this. In some sense, space and time really began to merge with one another at the turn of the last the turn of the 19th into the 20th century. And most famously, of course, we have Einstein to thank for really putting it together in its full glory to give us our understanding of gravity that we use today. But let me take a step back and just remind you of some of the concepts we're going to use. And I've drawn here a little bit of a grid, and that's meant to represent the space. It's really three-dimensional, but I'll draw it as two-dimensional, and I'll reduce the dimension even more in a moment. The space you can move around in, and there you are moving around in the space. And then there's a sense of time. As I move along, I can describe motions in the space. I can even put an axis to show time going by, and you have a series of snapshots of that motion. And so what I'll do is actually I'll say, well, I have time and I have space. I'll represent space just as one point on a line, although really, of course, it's three-dimensional. And I'll just write a little bit of a grid down and call that space-time, because the key idea is that space and time are really part of one thing called space-time. And in special relativity, what the realization, of course, was that the different observers, different states of motion, result in just different slicings of that single entity, space-time, in order to get what one person may call their space and their time. And then different slicings give different choices of space and time. And all of the business to do with time dilation and all of those things you may have heard of come from making those different slicings. Einstein then goes a bit further 10 years later in 1915 and tells us that gravity is really the dynamics of space and time. It's a really physical object that space-time can change its shape and size in various ways. And I've depicted that as a set of two-dimensional shapes that are trying to show you, because of the grid lines, the various kinds of shape changes that you can get. And that whole business of the warping of space-time is, of course, something that's very much in the popular consciousness in some of the contexts I already told you about. So once you start doing that, there's a lot you can do with your imagination, and we'll talk a little bit about some of that in a moment. But of course, it's important to remember that this isn't just a game of drawing pretty pictures. There's actually equations you have to solve, and those are the famous Einstein equations telling us exactly how space-time is allowed to do that in a quantifiable way. And so much of our modern physics, particularly in the context of astrophysics, but also cosmology, really is governed by that equation. One of the key things to do to appreciate, if you've never seen this equation before, is to sort of understand the left and the right side of the equation. The left side is essentially a bunch of objects telling you about the geometry, the shapes that space and time can have, which in the old language then would be the gravitational field, if you like, what gravity is doing. On the right-hand side is matter and energy, the stuff that's causing that shape change. And roughly speaking, you can divide things in that way to understand how the equation works. There actually are times when you move things from the left side to the right side, but let's not worry about that. Essentially, it's matter and energy on one side giving rise to changes of shape of space-time, which we interpret as gravity. So the classic picture would be that you have, in the old language, you would have, for example, that green blob there being some massive object like a planet. That orange dot is moving along, a few snapshots of its motion in time, and those red arrows would represent the force of gravity due to the presence of that object. That gets replaced by the idea, and you know, this is not a technical diagram. This is a cartoon of what's going on. Really, what's going on instead is that I have space-time. The blue stuff gets warped by the presence of the mass energy of that green blob, and the orange dot then trying to do what it likes to do, which is essentially move along the shortest path in space-time, ends up describing a bent path because of the warping of the space-time that you then interpret as a motion, an attraction towards that massive object. And that's essentially how that works. And it gives a beautiful picture and actually gives a more accurate description of physics than Newton's laws for gravity. Well, we're off to the races then. We can start drawing different shapes and imagining what they might mean. And you could imagine an extreme version of that warping that I just described, which you may have seen pictures like this before, representing something so extreme that the physics becomes quite extraordinary in the neighborhood of such a distortion, and that is going to be, for example, a black hole. Other things you might draw might be familiar as well. You have a bending of space-time that then connects back on itself, and that leads to the idea of a wormhole, which is, of course, something that shows up a lot in a lot of storytelling, and as far as we know, remains fictional in actual physics. So there are all sorts of interesting things that people talk about in popular culture: black holes, wormholes, time travel, the Big Bang, warp drive, gravitational waves. All of these things essentially come from those core physics concepts that came about at in the early 1900s. And I will talk a little bit about black holes. Actually, one thing I should do while I remember is tell you what my color coding means. I have some things in red, some things in blue, and some things in green. The color coding is fairly simple. The black holes are things that, the black holes, the Big Bang and gravitational waves are things that we have actually gone out there in actual scientific observation and verified that are real things. The red things are ideas that can come and have come from general relativity and related fields, but as far as we know, remain fictional. Time travel is a tricky one, so I've put it as green because it's sort of half true. In relativity, both special and general, there is a very well-defined and established experimentally notion of time traveling into the future. Time traveling into the past, however, is fraught with conceptual and logical difficulties, which may be resolved in some way. People actually do work on that, but as far as we know right now, seems rather difficult, if not impossible. So I color-coded it green as half true, if you like. Nevertheless, all of those things are exciting concepts that people use a lot in inspiring people about this area of science, and that is as it should be. So black holes, I'll talk a little bit about that. So you've probably heard a lot of things about black holes, and I apologize if I'm going to repeat a lot of them, but they are really exciting. There's all sorts of exciting things going on. I thought I'd talk a little bit about that so that I'm not just sort of talking generally about things and be a little bit more specific. So what I thought I would do is give you a list of handy facts that you can impress your friends with in the pub later on. Things everyone should know about black holes, if you like. Well, the key thing is, of course, what is the core idea of a black hole? And it's actually often not realized or perhaps forgotten that the key idea actually is very old. It actually goes back to the 18th century. It seems like a modern idea, but it actually has quite a history. But the core idea is, of course, to do with escape velocity. And of course, we all watch those amazing launches of spacecraft that happen where you're watching this rocket trying to escape from the Earth's gravitational pull. And the point there is that there's a particular velocity you must achieve, an escape velocity. And that escape velocity is really just coming from equating the kinetic energy to the gravitational binding energy. And so an object that has a particular amount of mass, which I've denoted there, capital M, and you're a distance r from the center of that mass, will have a particular escape velocity associated with it if you're trying to escape from that radius. Now, it was in fact, so I can actually write down what that escape velocity is, and it's a function of the mass. Now, it was actually back in 1783 when John Mitchell actually thought about this and realized that given the recent idea that light has a finite speed, he thought, well, if the escape velocity from a particular massive object, if its mass was in a small enough region, that capital R, the escape velocity could be so high that it would exceed the speed of light. And then that would mean you wouldn't be able to see the object. And so thus was born the idea of a dark star, as he called it, and that would be really interesting. And so he made a note about it in the literature, and it was largely forgotten about. I think Laplace later rediscovered it, the same idea, a decade or so later, and then it sort of lay there in the in the literature for a while as a sort of amusing idea, but we had lots of other things to be sorted out in physics before that could really be made sense of. But that was really the birth of the idea. The analogy I like to give, because it sometimes feels rather arcane, is the following. You have a river that you may be swimming in for some reason you're swimming near the waterfall that is at the end of the river, and it is the setup is such that there's a distance. The key thing is that you have a maximum speed at which you can swim in a given body of water. And so there's a close distance of closest approach such that if you get closer than that, you are never going to be able to swim fast enough to stop yourself from being swept over the edge of the waterfall. And so in some sense, the shape of the river is such that the speed of the flow gets faster as you get closer to the edge. And so you can imagine there's a particular place, which would be the horizon of the black hole in our analogy, beyond which, although nothing particularly horrible happens to you at that place, being there means, crossing that line means that you are doomed at some point in your future to go over that waterfall. So that's a reasonably precise analogy of the horizon, the distance at which you would approach the object, that distance r we talked about before, beyond which your escape velocity would have to exceed the speed of light. Now, this all gets firmed up quite nicely in the early 20th century because special relativity comes along, and first of all, in special relativity, the fact that the speed of light is a speed limit in some sense is confirmed, and so it means that a black hole is really quite a remarkable object because it's not just that light can't escape, but nothing can escape in that classical picture, because nothing can go faster than the speed of light. But then in 1915, general relativity, which I talked about earlier, comes along. Gravity is described as the curvature of spacetime. Those are those equations again. And one of the really remarkable facts in the history of all of this is that within a few months of Einstein publishing his equations, a young chap, Karl Schwarzschild, who's in the trenches, during World War I, writes down the exact solution. The first non-trivial exact solution of Einstein's equations actually is what's called the Schwarzschild solution, and it represents precisely that strange picture I drew before. Those are the equations representing that's the equation representing the Schwarzschild solution. I'm sprinkling equations back and forth. If you're not familiar with the language of those particular equations, don't worry about it. It's just to know that this isn't fantasy. It's the real solutions you can write down to these equations. So in the equations, you actually see that particular radius we had before, 2gm over c squared, where c is the speed of light. That is what's called the Schwarzschild radius, and that is the point of closest approach to that spherical object, the event horizon. One of the other things that it's nice to think about is how big a black hole can you make from some familiar object? And one of them would be, well, a very familiar object, Earth itself. So how small do I have to take the mass of the Earth? Into what radius do I need to compactify that in order to get the escape velocity to be the speed of light? And well, we can just put the numbers into that equation. We can just calculate. We know the speed of light, the mass of the Earth. These are all facts that you no doubt can all pull out of thin air, and Newton's gravitational constant g, and so you can go ahead and calculate. And if you did, that would be the result. It's about a centimeter or so. And you can do a similar thing for the sun, and it'll be about 3 kilometers. And so that's sort of interesting. So that's the idea, that's the extreme amount of compression you have to do to ordinary matter in order for this to make sense. And of course, if you think about it, especially in the early part of the 20th century, that just seems ridiculous, and a ridiculous amount of compression you would have to do. And so it took a long time for the idea of black holes to be accepted, because it just seemed so ridiculous, the amount of compression you have to do. But as time went on and people's understanding of the structure of matter, understanding of physics, and understanding of how to solve the equations of general relativity got better, it became more and more compelling that this is actually something nature is not only able to do, but in some sense must do, is driven to do in certain situations. And so famously Chandrasekhar showed that if you have sufficiently massive stars, there'll be a point at which, when they run out of their fuel, that supports them against gravitational collapse, when they stop that nuclear burning and they start collapsing, essentially nothing can stop them from collapsing to a black hole if you have a sufficiently large starting point. And of course, at the same time, research in astronomy was telling us about the existence of very, very massive stars. And so knowing that there are such massive stars out there tells you that astrophysically black holes are probably an inevitable thing. Nevertheless, by construction, they're going to be very hard to observe, and you shouldn't just take theorists' words for it. You should go out there and find them. And so we still had to wait some decades. So we have lots of artists' impressions of black holes. The idea that you could detect black holes, of course, starts becoming very seriously considered when you start worrying about what black holes do to their local environment. So even though the black hole itself is invisible, it does remarkable things to its neighboring stuff. And so these are all artists' impressions, by the way. Sort of, yeah. And so you might then wonder at what point you might then wonder at what point the evidence started pouring in, and well, that's a longer story. It's very interesting to see the shift that took place historically when people started gathering what we now think of as strong evidence. But if you're pushing back against this idea, they could be just circumstantial evidence. There's a longer history to give, which I won't go into here, but various kinds of objects, mostly to do with binary stars, where one partner is dumping material onto the black hole and then it's emitting remarkably in, for example, the X-ray spectrum, are examples. Other examples were the remarkable objects like what were originally called quasars, but we now generally call active galactic nuclei, telling you that there's some incredible engine needed to power these objects, to give them the sort of luminosity that they have. And the mechanisms people were coming up with in ordinary astrophysics were just not up to the job, whereas black holes really do a very good job of doing that. So I'm going to skip some of this, because, you know, time. And I'm going to go straight on to the idea of some of the evidence that began to come to light in more modern times, if you like. In the 1990s, one of the remarkable realizations was that, in fact, not just in active galactic nuclei, but pretty much in all galaxies, at the core, there are what are now called supermassive black holes. And one of the remarkable things is that you can really actually see the effects of these black holes by careful study. So this is actually from the center of our own galaxy. So this is from the UCLA group, and there's a little movie here I'm hoping I can get to work. And let's see. No, it didn't run. But let's try it again. So what we have here, there we go. What we have here are some stars which have been magnified to, so you can see them, at the center of the galaxy, our galaxy, and they're orbiting something. You can work out where it is by following the various trajectories, and they've nicely highlighted them for you. And you can see that you can deduce that they're orbiting a very massive, you can work out the mass from the trajectories, but you can work out how much that mass is concentrated, how small a region it's in, to deduce then that there must be something in there that constitutes a black hole simply because of the amount of mass that is in a small area, small region in the core of our galaxy. And this is, for our galaxy, we can actually image a lot of that very close up, and so really track those stars' trajectories. That's from the UCLA group that really has made a long study of those that region of the galaxy, and it's quite remarkable. That was sort of one of the, I think, stunning realizations in astrophysics, that black holes were so crucial to galaxies. And people are still trying to work out right now what that really means for galaxies. Are black holes crucial to the formation of galaxies right from the beginning, or do they form at some point during the galaxies already? The galaxy's already been evolving, and then the black holes form, and so on and so forth. The dynamics of galaxies has really been changed, and of course, galaxies are our home. So that's quite a remarkable change in the role of black holes in our everyday lives in some broad sense. The recent really big excitement with black holes was with being able, in some sense, to see them directly. And this relates to LIGO, the gravitational wave detections that were announced in the last couple of years. So there's a picture of a couple of the gravitational wave detectors that make up LIGO. And essentially, this uses this other aspect of space-time that I told you about, which is that it's flexible. One of the other predictions from Einstein's equations is that ripples in space-time move with the speed of light outwards. They're not light, but they move with the speed of light outwards, and we could, in principle, detect those gravitational waves. And as you may have heard, that was indeed successfully done, announced in 2016. And the remarkable thing is that the first things that were seen were collisions between black holes. So finally, in some sense, we have direct evidence of black holes, because we're getting now radiation, albeit in the form of gravitational waves, from those black holes as they collide, as they merge. And I'll show you a picture of that in a moment, a picture, quote unquote. Those are some of the gravitational wave detections of LIGO. That's a poster that if you don't already have up in your department, I strongly recommend having up. I think you can just order it from LIGO. Here is actually a simulation of two black holes merging. I think this is from one of the LIGO groups. And what it actually is, of course, because we don't have cameras looking at the black holes nearby. What it actually is you put all of the you put the equations of Einstein on a computer. It solves the equations. It even traces the light from distant objects, the star field behind, to show you how that gets distorted as it's passing through this region of the merging black holes. So this is the best we can do in terms of a picture of what's going on. And there are the two black holes orbiting each other. And energy is being emitted in the form of gravitational waves that eventually we detect a few billion years later. And the orbits decay, and these guys get closer and closer, orbit faster and faster, and then they merge. And so that's really what's going on. We're now seeing that this is actually something that is happening all around for what are called a certain class of intermediate mass, or slightly lower than intermediate mass black holes, a few tens of times the mass of our sun, which is a whole new class of black holes that had not really been studied much in astrophysics. So real excitement, new class of black holes being discovered, and being able to see them directly, and actually being able to see them dynamically merging, and the output of that. The output of that's actually rather interesting. I realized I had a little bit of sound, and I forgot to connect it up. Never mind, you can imagine it. What you can actually do, I'll just describe it before I show it. What you can actually do is take the signal, the gravitational wave signal, the distortion of space-time that we detect locally, which in those gravitational wave detectors is really detecting the relative change of two long arms that are arranged perpendicular to each other. You detect the relative change of those two arms and turn that into a signal. You have two sets of those widely separated, so you can subtract out any local noise. And then you look for a similar waveform in those two machines, telling you that something far away is happening for real, and not just a garbage truck going by outside. What actually happens is that as I said, remember, the black holes speed up as they lose energy because their orbits are decaying, and so that gives you what's called a chirp sound, because it sweeps from lower frequency to higher frequency. And if I had connected the sound, you would actually see that chirp sound, but there it is. And so it goes a sort of whoop sort of sound, and slightly different from that. So that sound is, that chirp, it's really the sound that you hear of, quote unquote, of the black holes merging. That's really the characteristic, that the actual waveform, something that had been solved for in the equations numerically as a prediction of what that would be like if black holes were merging. And then they really saw it in the experiments. It's sort of it's a textbook example of how this is how science works in terms of the dialogue between theory and experiment. Since then, there have been remarkable observations also of neutron stars merging, which I don't have time to talk about, but is quite a remarkable and very important discovery. In some ways, and you could argue about this, in some ways it's more exciting than the merger of black holes, because there's potentially more information about a wide range of astrophysics from colliding neutron stars. Because what happens is that you have the neutron stars collide and you get the gravitational waves from that, but you also get a lot of things happening in the optical as well, and in the electromagnetic spectrum. So you have across across the electromagnetic spectrum, you have interesting things happening. So typically, the state of the art is going to be that there's gravitational wave detectors will observe neutron stars about to collide. They will send signals to telescope counterparts around the world, terrestrial and space-based, saying, look at that patch of the sky, or as good as we can guess where it is based on the gravitational wave signal, because something spectacular is going to happen. Train all your telescopes in all spectra on that and learn a huge amount about the physics of that event, all within a few milliseconds. These coordinations will happen. And so that is the birth of what's called multi-messenger astronomy, where we're having all of these different ways of looking at astrophysical objects to learn a huge amount about astrophysics. So in some ways, arguably, colliding black holes are maybe not as exciting as colliding neutron stars for the wealth of astrophysics that you might learn in that way. But many of us are excited about being able to see black holes merging in this way, because they may start giving us clues about the structure of black holes. They're much more interesting and have to be more interesting than just these perfect spherical non-radiating objects. And that's because actually when you start including quantum physics in the story, as is inevitable, you realize, as Hawking first did, that black holes actually aren't black. They actually, when you interact with the quantum aspects of our world, you realize that there's a little bit of a competition, and the quantum world must win. In some ways, as you know or have heard, the vacuum, quote unquote, empty space, is seething with possibility in the quantum world. There's pair creation. There's a probability that a particle-antiparticle pair can pop out of the vacuum and then disappear, annihilate again. And that's happening, in some sense, all the time, everywhere, with some probability. Then you bring in this idea that, there's actually a one-way barrier, that event horizon. And these two things can't both be true. So when you think about it, as Hawking did, and you ask what happens if you have a black hole horizon in this seething possibility of pair creation, you get the following. So let's see if this works. There's the horizon, and there's a pair. There's a pair created. One of them can fall behind the black hole horizon, and then the other one is free to fly away. It's no longer a virtual quantum ghost of a thing. It's a real thing that can be detected out there beyond the black hole. And when you actually do the arithmetic and add it all up, what you find is that that's equivalent to a black hole actually radiating quanta, particles, out to infinity that you could actually detect in principle. And that is what is actually known as Hawking radiation. So you can actually go and compute the Hawking radiation. I give you the equation there. The key thing to see is that it goes inversely with the mass of the black hole, and there's an H bar on the top line, which is telling you that it's an intrinsically quantum effect, and that quantum effect is, if you like, one of the first things we realized, first concrete results of quantum gravity. So the implication, it turns out to be rather profound when you run through it. And it actually began a little bit earlier than Hawking with Bekenstein. Black holes, in some sense, are behaving when you put them together with quantum physics, they're behaving like thermodynamic objects. They have a temperature, they have an entropy, and you can write down things like the first law and the second law of thermodynamics for these objects. And that, if you take that seriously, is telling you something very important. It's telling you that just as with an ordinary thermodynamic object in ordinary physics, if it has an entropy associated with it, that's telling you that there's some microscopic internal structure. That entropy is telling you about the different arrangements of that internal structure. And so what is that internal structure for a black hole? And that's a big question, because it's telling you that there are degrees of freedom that are intrinsically quantum mechanical, but have to do with gravity, that the black hole physics knows about, that is in some sense giving you the internal structure of the black hole that macroscopically then looks like this thermodynamic physics. And so that's one way into understanding the long sought after quest to understanding quantum gravity. So black holes turn out to be key in that quest, and it is rather nice to know that we can see black hole horizons actually merging and forming new black holes in real observations, in real experiments, because it's a sort of dynamic window that we haven't had before. Now, I should say that the fact that black holes have a temperature, if you actually calculate that temperature for astrophysical black holes, if you calculate what that structure for black holes might be, that internal structure, it's extremely inaccessible. The temperature is for any astrophysical black hole is way smaller than even the temperature of the cosmic microwave background, the temperature of the universe itself. So that's all very suppressed in the noise of everything else in the universe. We're not going to measure Hawking radiation anytime soon, and we're not going to measure the internal structure, if it exists, of black holes by any stretch of the imagination real soon. But in principle, it's there. And as we're understanding more and more about real black holes and understanding the range of possibilities of sizes of black holes that play a role in our universe, I think we're going to get closer and closer to being able to find the right kind of questions to ask about real black holes that may begin to tell us something about the quantum aspect of black holes, if we're lucky. So I think that's a really exciting area of research that I should make sure I leave you with. Now, I'm going to now do a change of direction and tell you a little bit about, just forgive me for a moment, I'm just going to skip some slides, and I'm going to tell you a little bit about the other stuff that I promised. So we have all of these different things, and as I said, they're really part of the language of storytelling that's out there, all of these different things. And I thought it would be fun to tell you a little bit about the work that I do that helps some of those storytellers. Now, the context, we're all here today because we're excited about the mission of getting people interested in physics, excited about physics, and this is one of the ways that I like to get involved in that mission when talking about engaging the general public. Some people ask why I do this sort of thing. Why do I mess around with all of these silly, frivolous things when I should be doing, serious research and teaching? And the point is that that's, at least for a large portion of the day, where a lot of people's eyeballs are. That's where people's attention happens to be, and it's in the entertainment. So it just seemed as a matter of just being practical, if you want to get people's attention, go to where they're looking, and they're looking at this stuff. So let's put some physics in there. So these are examples of the various shows and movies. in which you may have seen, in some cases probably to your annoyance, various physics terms, various, not just physics, but science in general, being bandied about. And yes, it's not always accurate. But the point is that there's a chance that you inspire some people. You get some people asking questions, and that's usually my goal. Unfortunately, when people, especially in the press, write articles about this kind of work, they insist on using this word accurate. Science advisors are helping movies get the science more accurate, and that's just setting everybody up for failure. That it's nice if you can do that, but that isn't the point. So yes, it can be a bit unfortunate. But there are things you can do that are getting those storytellers more involved in two things. One is less making up random bits of science, just randomly with no sort of internal structure, and paying attention to things like internal consistency and things like that can help you tell a better story. They're not interested in doing a physics lecture, and that isn't the point. They're interested in selling a $15 or $20 movie ticket for you to come and sit for 2 hours and be entertained, and maybe tell your friends that it wasn't a total waste of time, so that they go and spend money on a ticket. So what you've got to do is help them find at least a way of not having people put aside their suspension of disbelief. So make things more believable, if not accurate, at least believable. And so that's an interesting thing that you can do in the context of a film, or actually it's some ways more rewarding over the course of maybe a TV series, because you have a longer arc of things you can do. And so in all of those cases, depending upon what they need, it's usually an attempt to do a dialogue with those filmmakers to help them understand some of the exciting things that can come from science that they can embed in their story. So that was the wormhole from Interstellar, which I was not involved in. That was Kip Thorne worked on that film. But trying to get them trying to inspire, for example, this is the Thor movie from last year. There's a really great conversation about the concept of wormholes. And I ended up talking with the director and then the VFX people about how those things may look, inspired by some of the astrophysics that was going on. These wormholes connect to various astrophysical objects in the distance, and then how the physics of the atmospheric conditions around would interact with the wormhole entrance. I spent a fair amount of time trying to convince them that they should make wormholes spherical, and unfortunately they didn't go with that. But there you go. You do what you can. But one of the great things is that in addition to that, I get to help them make one of the characters, who's actually a scientist, Bruce Banner, actually sound a little bit more like a scientist. So he says things that make him arguably more believable as a character who's actually an astrophysicist, and so on and so forth. This is from Agent Carter. There's actually a lot of really great opportunity. There were actually a lot of great opportunities for putting physics into this. One of the things that was also fun for those of you who may or may not have seen it, or may see it one day, is that I also put in, because it's actually a period piece, it's sort of just after World War II in the 40s and 50s, and the science investigators, I actually put physics on the blackboards that are actually period appropriate, which was actually sort of fun. So the kinds of things they were trying to do to understand the exotic matter that lady is manipulating there, they're trying to think things they're trying to understand about its effects, they write equations that actually were using some of the models of the time about the structure of matter. So that was sort of fun. Okay, I should speed up a little bit. One of the famous things that people love in the Marvel universe is speculating about the nature of Thor's hammer. And that leads to some great conversations about, well, electricity and magnetism and so on and so forth, but also about exotic materials, because famously Thor's hammer is very heavy, and there have long been speculations about, well, maybe it's made of neutron star material. So you get this obviously utterly ridiculous idea dressed up in this story, which is rather nice, but it gets people inspired to think about, well, what is a neutron star? And maybe you hope that people might go and Google it afterwards at least, and then start getting excited about some of the ideas. So let me jump a little bit. The last thing I'll mention is in the latest Infinity War movie. This is the Avengers. One of the fun things there is the whole business of these. This is not a spoiler. These artifacts left over from the Big Bang. They're called infinity gems or infinity stones, and they have various characteristics of the universe. Each one has a sort of specialty, if you like. And, you know, it's all an adventure to do with some being trying to get hold of all of these stones to control the universe and blah, blah, blah. And it's all very fun. Actually, very well done film. One of the fun ideas that this resonates with that I like is the fact that, of course, in real physics, we do play with artifacts from the early universe. In particle physics, we really are recreating the conditions soon after the Big Bang and searching for fundamental particles that, in some sense, are messengers of those early essences of how the universe worked, the Higgs boson and things like that. So it's always, you always get, you know, even if you're not going to get someone stand up and say that in a movie, there's opportunities to help them hint at that as you go along. So let me try and sort of scoot along to the end. A lot of times I you know, if they'll listen, I'll sketch them ideas and designs. Sometimes those things actually end up being made, sometimes to my surprise. And it's all very interesting, this dialogue between the entertainers and the scientists like myself. And there are other, you know, there's fun things you can embed, but there's also, in some ways, I think some of the most important things you can do is also give them better images of who scientists actually are. Because typically, when you think of scientists, you have the crazy old man with white hair image attributed to Einstein. And so, for example, this was in the National Geographic series on Einstein's life. I get to work with the filmmakers and say, no, look, let's spend more time showing that Einstein was a young, very sort of not the sort of socially awkward, sort of geek kind of image we have of scientists, but a very personable young man who had friends who he interacted with. He wasn't just this genius in isolation, just coming up with stuff randomly from the ether. He was actually interacting with people and part of a community of scientists. These are really important things to show, and in some ways I think these are much more important images to get accurate than whether or not, you know, you can actually make a hammer out of a neutron star or not. And so I spend a lot of time trying to give them better images or if you like, more diverse images of the kinds of people who can be scientists in their stories. And I think in some ways that can help with the whole mission that we're all trying to do with getting people excited about science, getting people engaging with science, helping them realize that they too can take part in the conversation about science. So I think I'll stop there, and I don't know if there's time for questions, but if there are, I'll take some.
I believe we do have time for a few questions. Does anyone have a microphone out there? Yes, thank you. There's one right here.
Hello.
Hi.
How do you go about getting into advising for popular culture?
That's a great question. The short answer is it takes a lot. It takes time. You sort of have to build up a relationship, and then people pass your name on to other people and what have you. I think during the time I was first doing it, there was no real structure for doing that, and I think just by word of mouth and things like that, people heard that I like doing that sort of thing, and then if you do a good job elsewhere, maybe someone mentions it. One of the problems is that the industry itself doesn't actually have a slot for a science advisor, so you sort of end up, no one really knows what that is, and everyone disagrees about exactly what that is. So that can be quite difficult. But I should say one of the things that has come along in recent times has been something set up by the National Academies of Sciences called the Science and Entertainment Exchange. Sorry, I'm doing this because the lights are in my eyes. I'm trying to see you. So if you look up the Science and Entertainment Exchange, they actually are very good at connecting storytellers to scientists now, and they're getting better and better at that. They even have a number 1844 need sci, and they'll connect you to a scientist if you tell them what you're working on. So that came along relatively late in the game, but I think that has been now one of the main movers in making these sorts of connections better, and that means that now there are many more scientists who can get involved and immediately start connecting to people in the industry. And I should say it's not just films, it's not just TV, it's also books, video games, things like that. I'm talking, for example, with the best-selling author Blake Crouch right now about his next book, and he tries to embed physics in there, and people really love it and apparently buy lots of copies. So you can make a difference in many aspects of the industry, either with their help or through being on social media or blogs and things like that. Hi.
What's the estimated predicted time to convert sun into black hole?
Could you use the microphone, please?
I said, what's the estimated predicted time to convert our sun into black hole?
Oh, you mean when would it happen for our sun?
Yeah. Okay. Future.
Yeah. So, right. You're worried about investments and things like that, right? Yeah.
Yes, please.
Yeah. So
estimate.
The estimate would probably be infinity, because our sun is actually rather small, and so it probably isn't massive enough. Even if it did run out of fuel, it probably isn't massive enough to form a black hole, and so it'll probably die in a more mundane way.
We have time for one more.
A wonderful presentation, thank you. Several years ago when Interstellar was coming out, they were supplying all these posters talking about with Kip Thorne prominent there, right? And I have been a follower of Kip Thorne's career and just think he's just really good. But I saw that movie, and I got to tell you, where was this accuracy of science? I mean, from a planet that, we're having a little problem with light for corn, so we've got to go through a wormhole in order to survive. to a glowing black hole that was somehow lighting planets. And I just wondered if you had any comments on that. Maybe you don't want to say, because I assume you guys may be related, but I felt very disappointed as a teacher. I had promoted this. They sent these posters to all of us in high schools. We posted them all over. We got kids to go watch this thing, and then we had to explain why it was so much what it was.
Right. So, so I, of course, wasn't part of that that whole project. But I can make some guesses based on my own experiences with other films. I can make some guesses as to what happened in terms of the promotion, because one of the problems is that the PR people, have their own agenda, and so I think they really they overstated this whole accuracy thing, probably to the embarrassment of people like Kip and probably even Chris and Jonathan Nolan, the writer-directors. And so the accuracy thing was really just oversold, and so it meant that they raised expectations too high, and we all went to see it, and yeah. On the other hand, there's a core thing which I think was wonderful that the film deserves a lot of credit for, and it's something that I had spoken with Kip about many years previously. Was saying, wouldn't it be great to, rather than have filmmakers just making up weird and wonderful stuff about nature, wouldn't it be great if we could show, and by we I mean scientists, could show filmmakers that you can take something like general relativity and show that there's incredible weird and wonderful stuff that's true. So the core some of the core things that were done in Interstellar were, I think, remarkable in that spirit. So one of them, for example, is gravitational time dilation. Right? So we get to teach people about gravitational time dilation and tell them it's a real thing, because GPS wouldn't work without it. And I'm sure we've all done this in our classrooms, and if you haven't, you should, because it's an amazing thing. It really is time travel into the future. Right? One of the things they do in Interstellar is they take an extreme version of that. They have a much more extreme gravitational field, and so you see that some people leave the spaceship and go down to the surface of a planet and come back up a few hours later, and 22 years have gone by on the spaceship. And the point is that that's one of the places people most often point and go, well, that's just made up, isn't it? And you get to go, no, that's a real thing about gravity. And that's a great thing to have in a major film, to get people talking about. So Interstellar is full of things that you can point to and go, there's some great gems here, sort of talking points for teaching. But overall, the arc of the movie is a mixture of fiction and made up stuff and what have you. Kip actually has a really nice book called The Science of Interstellar, where he goes through and he talks about all the different scientific things, and he color codes them or flags them. I can't remember. Maybe he has a letter on the page or something that says whether this is, real, made up, kind of true, what have you. And he sort of goes through and he talks about the struggles he had with the Nolan brothers to sort of stay on track, because they sort of made a deal at the beginning about trying as much as they can to be quote unquote accurate, but knowing that sometimes you're doing some drama. And so, I think for me the problems with the movie were less to do with the extrapolations they did with the science, and more to do with the actual basic human storytelling. I think that's where the film wasn't as strong as I would have liked. No disrespect to the Nolan brothers, who I think are wonderful storytellers, but I felt the human side was more problematic than the whether or not the wormhole, what have you. So, and then the other famous thing I should say is that's quite remarkable is the work they did on the supermassive black hole. That was actually one of the first times, that was the first time that the actual visuals as to what a supermassive black hole with an accretion disk would actually look like. They actually worked it out in great detail using, Hollywood computers as opposed to, you know, the meager resources we have in science. And no, it's a serious point that, you know, it hadn't been done before because it was too expensive. But they had the special effects level computers to do it. And when you do it, you actually get this bizarre and beautiful shape that you see in that film. And they wrote scientific papers about it. It was actually the first time that had been worked out. So some actual real science was done to get that movie to work as well. So, you know, it's a film that gets a hard time because of that overselling of the accuracy point. But actually, I would say there are some gems in there in terms of teaching points, teaching moments for physics.
Probably don't have time for more questions, but Dr. Johnson will be here for a few minutes afterwards. You want to call him and ask him something. Can we thank our presenter again?